Now that we have seen how to solve problems on ladder friction, let's look at the case of wedge friction. As you know, wedges are usually of trapezoidal or triangular cross-section. They are used to slightly lift heavy weights like machine parts or precast beams for final alignments or to make place for inserting lifting devices. The weight to be lifted would be of a greater magnitude, so in most cases, the self-weight of the wedge is neglected. Now look at this figure where we have a body of weight W which has to be lifted up by a trapezoidal wedge which is being driven beneath it by applying a horizontal force P. When you look at the figure, you find that there are three different surfaces of contact. The first surface, surface number 1, being the contact surface between the wedge and the horizontal force along which the wedge slides. The second surface is the surface of contact between the inclined face of the wedge and the body. And the third surface is that between the body being lifted up and the vertical wall or the vertical surface along which the body is sliding upwards. And obviously, along all these three surfaces, we have frictional forces acting, and let mu1 be the coefficient of friction at the surface 1, mu2 that of 2, and mu3 that of 3. Now, before analyzing the system, you need to understand that when limiting force of friction develops, the system would be on the verge or on the point of motion. Till then, the body or the system would be in equilibrium. This is what we are analyzing in wedge friction. The temporary equilibrium of the body and all the surfaces which are in contact just before it is being lifted up or just when the limiting force of friction develops. So we need to consider the equilibrium of the body and the wedge and the surfaces of contact along with all the forces acting in the system. So what are the forces acting on the system? To analyze those, you need to draw the free body diagram of the body being lifted up and the wedge separately. Let's see how the free body diagram looks of the body, the FBD of the body. We have the body as this. This is the body. The first force is clearly the weight of the body which has to be lifted up, or W, which is acting vertically downwards. Now, we have the surface of contact 2. We have named it as 2. The surface of contact 2 between the body and the wedge where the friction is mu2. So along the surface, we have the normal reaction. Normal reaction means acting normal to the plane or acting vertically upwards. Vertical to the plane. The plane being inclined at an angle of theta. Remember, this theta is the angle of the wedge or the angle of inclination of the plane of the wedge to the horizontal. So here, perpendicular to the plane means it would be at theta degree to the vertical. So that would be the normal reaction. Since the surface is 2, shall we name it as R2? Okay, R2 acting like this. Self-weight acting vertically downwards. And now we have the friction developed along the surface. How does the friction act? Friction always acts in a direction opposite to the direction in which the body tends to move. How does the body move? When the wedge is driven towards the left, as shown with the force P, when the wedge is driven towards left, the body would slide upwards. When the body slides upwards, the friction would act downwards along the surface of contact. So this would be the friction that is developed, and we know that F2 is equal to mu2 R2. Alright. Now we have the third surface, which is the surface of contact between the body and the surface along which it is sliding up, where we have the normal reaction. Since the surface is 3, we'll name it as R3. And obviously, since the weight is being lifted up, the friction would act along the plane down. So this would be F3 is equal to mu3 R3. So we have drawn all the forces acting on the body here. What are those? We have the self-weight acting vertically downwards. We have the normal reaction R2 along surface number 2, perpendicular to the inclination, or rather at an angle theta with a vertical. And since the body is sliding upwards, we have the friction acting downwards, and F2 is equal to mu2 R2. Then we have the normal reaction 3 at the surface, R3 at the surface 3, and obviously the frictional force F3 is equal to mu3 R3 acting downwards as the body is lifted upwards. Clear? Similarly, before considering the equilibrium of the body separately, let's draw the free body diagram of the wedge as well. And we'll consider the equilibrium separately after that. I'm drawing this together so that you understand how the reactions act along the surfaces of contact. So we have the wedge like this. We have the wedge. And look at the forces acting on the wedge. We'll consider the surface number 1, the surface of contact between the wedge and the horizontal floor. We have the vertical reaction at 1 R1. We have the force to be applied on the wedge to drive it so that it lifts the body up. And since the wedge is being driven towards the left, we have the friction F1 along surface 1. And since this is R1, F1 is equal to mu1 R1. And we have, see, at the surface 2, the body and the wedge are in contact. This surface and this surface, even though we have drawn it separately, these are the same. We have drawn it separately, but these two surfaces, this is surface number 2, this is also the same surface. So the reaction R2, which is acting upwards for this plane, would be the same reaction R2 considered downwards for the wedge. It's the same R2, but it's considered as acting upwards for the body, whereas the same R2 is considered as acting downwards for the wedge. Again, the F2, which is acting on the surface 2, this being the same surface 2, the same F2 should be considered for the wedge as well. This is acting downwards along the inclined plane for the body. The same F2 is acting upwards along the same inclined plane for the wedge. So F2 is equal to mu2 R2 would be acting like this. So look at the figure. R2 acting in this fashion for the body. The same R2 acting along the same line of action for the wedge. F2 acting like this for the body. The same F2 acting along the plane but in the opposite direction for the body. And we have the horizontal force P, and we have the vertical reaction R1, and we have the friction F1 along the surface 1. So let's once again look at the total forces which are acting on the wedge. At the surface 1, R1 and F1. At the surface too, R2 and F2. The only difference being those are acting in the opposite direction as that of the body on the wedge. And we have P, which is the force to be applied on the wedge to drive it so that the body gets lifted up. Now we'll consider the equilibrium of the body and the wedge separately. Sorry, I forgot to label this FBD of the wedge. So we have the FBD of the body and the FBD of the wedge drawn here. Now, considering the equilibrium of the body, we have the two conditions of equilibrium, sigma Fx is equal to 0 and sigma Fy is equal to 0. That is, if you resolve all the forces in the horizontal or in the x direction, they would add up to 0, and similarly you can resolve all the forces vertically as well. Considering the equilibrium of the body, what are the vertical forces acting? W is a vertical force, mu3 R3 is a vertical force, and R3 is a horizontal force. But R2 and F2 have to be resolved in the horizontal and vertical directions. See, since the angle of the wedge is theta, the vertical angle, this would also be theta, and obviously this would also be theta. Now simple resolution, simple math. Since this is R2, the vertical component would be upwards, and this would be R2. Closer component is cos component R2 cos theta. And the horizontal component would be, see, R2 sin theta. Okay. Now for F2 or mu2 R2, this angle is theta. So the horizontal component would be, I'll write it as mu2 R2. Mu2 R2 cos theta. And the vertical component, the arrowhead is like this. So this is how you resolve it downwards. So this is mu2 R2 sin theta. So look at this. We have R2 cos theta acting upwards, mu2 R2 sin theta acting downwards, R2 sin theta acting towards the left, mu2 R2 cos theta also acting towards the left. Clear? So the horizontal forces R3 minus R2 sin theta minus mu2 R2 cos theta is equal to 0. Now dissolving all the forces vertically, we have mu3 R3 acting downwards, W acting downwards, mu2 R2 sin theta acting downwards, and R2 cos theta acting upwards. So you can write R2 cos theta minus mu3 R3 minus mu2 R2 sin theta minus W is equal to 0. So these are the two equations. Two equations. W would be known to you, theta would be known to you obviously, and mu1, mu2, mu3 all would be known to you. So we have R2 and R3 as the two unknowns here. So you can solve for it. Now we'll consider the equilibrium of the wedge. The equilibrium of the wedge. Just as what we have done here, we can resolve all these 5 forces in such a way that all the forces are either horizontal or vertical. P is purely horizontal. F1, mu1, R1 is also horizontal. R1 is vertical. You need to resolve R2 as well as F2. So this is theta and this is theta. The resolved component of R2 in the vertical direction is, this would be R2 cos theta, and this component would be r2 sin theta, and for F2 this would be F2, or rather I'll write it as mu 2 r2 cos theta, and we have, since it's directed like this would be the component mu 2 r2 sin theta. R2 cos theta is acting downwards, okay? Mu 2 r2 sin theta is acting upwards. So sigma fx is equal to 0. We have r2 sin theta, mu 2 r2 cos theta, and P along with mu 1 r1 as the horizontal forces. So you can write it as r2 sin theta plus mu 2 r2 cos theta plus mu 1 r1, 1, 2 and 3 is equal to 0. Well, did we miss out the most important force? Minus P is equal to 0. So it's like, once again, r2 sin theta plus mu 2 r2 cos theta plus mu 1 r1 all acting towards the right, and P acting towards the left. So it is like minus P is equal to 0. Similarly, sigma Fy is equal to 0. R1 is acting upwards, r2 cos theta is acting downwards, and mu 2 r2 sin theta is also acting upwards. So it's like r1 plus mu 2 r2 sin theta minus r2 cos theta is equal to 0. So we have two equations here. The r2 we have already found from here. You can substitute that r2 here. Mu 1, mu 2 and all are found out. We have two equations. Only r1 and p are the unknowns. Two equations, two unknowns. You can solve for p. So from these two equations you can find out p if p is the unknown. So that's how you solve problems on wedge friction. It could, at times, W would be known and P would be known, and you would be required to find out the angle of the wedge. Whichever be the case, these are the two sets of equations. Equilibrium of the wedge and the body, which has to be considered separately by drawing the free body diagrams clearly and analyzing it. Alright?